Good morning. So, today what we are going to discuss about is the Hyperbox Classifier, and earlier we had just introduced the problem in the sense that so far the kind of classifiers that we have talked about, it separates between two classes or the regions belonging to two classes which are simply connected, in the sense that if I have a set of feature vectors belonging to two classes which are given in this form. Again, I am taking this example in 2 dimension, having two feature components x 1 and x 2, and if the feature vectors or the training vectors belonging to two classes, say omega 1 and omega 2, they form clusters like this. So, this is one cluster, this is another cluster, where one of the clusters is taken from say class omega 1 and the other cluster is formed by the points taken from another class say omega 2. Then the regions belonging to these two different classes omega 1 and omega 2, they are to be simply connected, or I should be able to have a simple boundary, either a linear boundary or a nonlinear boundary separating these two classes. Okay. So, either I can have a boundary, a linear boundary something like this, okay, in which case the classes will be called linearly separable, or I should be able to have a nonlinear boundary something like this, in which case the classes are linearly non-separable. So, I should be able to have either a linear boundary or a nonlinear boundary. So, accordingly, we have talked about different types of classifiers, starting from our Bayes classifier, whether it is Bayes minimum risk classifier or Bayes minimum error classifier and so on, where we have seen that in a particular case, when all the classes have the same covariance matrix, or the points taken from all the classes, they have the same covariance matrix, and at the same time the feature components are statistically independent, or different feature components are statistically independent, then we can have a linear boundary separating the two classes omega 1 and omega 2. Okay. But in general, if different classes have arbitrary covariance matrices, or points belonging to different classes have arbitrary covariance matrices, in that case the classes are not linearly separable. So, we can have a nonlinear boundary, and mostly what we have is a quadratic boundary. And then we have discussed about the other approaches for designing of linear classifier, like perceptron criteria based approach, or relaxation criteria based approach, or minimum square error based criteria based design approach. In all these cases, we have talked about how we can design a linear classifier that separates two different regions by a linear boundary. Okay. And lastly, what we have talked about is the neural network approach, where if I have a single layer perceptron or a single layer neural network having multiple number of outputs, then what we have is we separate the classes where the classes are separated by linear boundaries. Okay. But if the classes are not separable by linear boundaries, in that case we have to go for multi-layer neural network or multi-layer perceptron, in which case the non-linear boundaries are actually replaced by piecewise linear boundaries. Okay. So, this multi-layer neural network, what it does is it approximates the non-linear boundary by piecewise linear boundaries. Okay. So, in all these cases, the regions belonging to different classes, they have to be simply connected. Okay. But as we said earlier, that if we have a point distribution belonging to different classes something like this, So, say these are the distribution points belonging to two different classes, okay, where you can assume that all the red points they belong to one class, whereas the green points belong to another class. Okay. Not only that, I can have some arbitrary distribution something like this as well. So, I have a set of points somewhere over here which belong to one class. Okay. I can have set of points somewhere over here that belongs to the same class. I can have another set of points somewhere over here which also belong to the same class. Okay. And in between I can have, so this is the set of points which belong to one class. This may be the set of points that belong to some other class. Okay. This may be the set of points which belong to some other class, okay, or this set of points may even be extended like this. Okay. So, if the point distribution is a complicated point distribution something like this, you will find that neither a linear boundary, obviously a linear boundary cannot separate among these classes, even a nonlinear boundary is also unable to separate between different classes. Okay. So, how we can design a classifier that can even classify the point distributions or the class distributions which are given like this. Okay. So, I just pointed out during our introductory lectures that we can go for a set of hyperboxes. That is, what I do is you divide this space into a number of hyperboxes something like this. Where different hyperboxes may be having different dimensions. Okay. Similarly, over here okay. So, in this two dimensional example, I can assume that those hyperboxes are represented by rectangles. So, I have a set of rectangles which represent one particular class. I have another set of rectangles which belong to another particular class. Okay. And if somehow we can assign the class level to these different rectangles. Okay. So, I can say that these are the rectangles which represent class say omega 1 and these are the rectangles which represent class omega 2. Similarly, I can have a set of rectangles over here that will represent class omega 3. I will have a set of rectangles covering this region which will belong to class omega 4 and so on. So, during the training process, during the training of the classifier, we have to identify this set of rectangles or the set of hyperboxes. Okay. So, next time during the testing or when you actually go for classification of unknown feature vectors, I simply see that what is the position of the unknown feature vector with respect to these hyperboxes which are already generated. Okay. So, if the unknown feature vector that falls somewhere over here. So, this is the location of the unknown feature vector. Okay. Then I can immediately say that because this unknown feature vector is lying within a rectangle which is labeled as class omega 1. So, this unknown feature vector also belongs to class omega 1. Okay. Whereas, if the unknown feature vector falls somewhere over here, okay, then immediately I can say that because this unknown feature vector falls within a rectangle which is labeled as class omega 2. So, this unknown feature vector also belongs to class omega 2. Okay. So, that way I can define or I can generate a set of hyperboxes based on the training samples which are given, and those hyperboxes are given the class levels based on from which training samples or the training samples belonging to which class that particular hyperbox has been generated. So, that becomes the class level of that particular hyperbox. And once I get the class level of the hyperboxes, then while testing or while in actual operation, I just find out that in which of these hyperboxes that unknown feature vector is situated. So, this unknown feature vector gets the same class level as that of the hyperbox. Okay. So, these hyperboxes are to be generated during the training operation of the classifier. Okay. Now, suppose I have a situation something like this. So, I have one hyperbox somewhere over here. Okay. Now, what is the advantage of these hyperboxes or the advantage of the rectangles? Once I divide the space, the feature space into a number of hyperboxes or into a number of rectangles, you find that such rectangles or such hyperboxes can be defined using just 2 points. Okay. If I know what is the left bottom point, okay, and if I know what is the right top point, that is sufficient to define the hyperbox. Okay. So, one of the points, this point, the left, because if I plot it against our conventional 2-dimensional coordinate system, so this is my x1 feature, this is the x2 feature. Okay. You find that corresponding to this left bottom point, both the features x1 and x2 they are minimum. Okay. Similarly, corresponding to this top right point, both x1 and x2 feature values are maximum. Okay. So, accordingly, this point is called a mean point, and this point is called a max point. Okay. So, once I define this rectangle or the hyperbox using this mean point and max point, such hyperboxes are called mean max hyperboxes. Okay. And to see whether an unknown point is within this min max hyperbox or not, suppose this mean point is represented by vector v, which will have x1 coordinate and x2 coordinate, which are minimum among all the points, and it is also represented by max point, which is say w, which also has x1 coordinate and x2 coordinate, which are maximum among all the points within this hyperbox. Okay. Now, so similarly, if I have n dimensional feature space or the feature vectors are n dimensional feature vectors, then all the n coordinates for this mean point will be minimum among all the points. Similarly, all the coordinates for the max point, all the n coordinates for the max point will be maximum among all the feature vectors which are given. Okay. So, if I say that a point P, I want to check whether a point P belongs to this hyperbox or not. Okay. So, let us consider the ith dimension. Say I have this unknown point P, and I want to check whether this point P belongs to this hyperbox or it does not belong to this hyperbox. Okay. So, suppose let me take that P I to represent the ith dimension of this feature vector P. It is ith dimension. So, 1 out of that n. Okay. Similarly, for the mean point, say V I represent the ith mean point, that means the minimum value of the ith coordinate. Similarly, W I represent the maximum value of the ith coordinate. So, this is ith dimension, ith component of the max point. So, if this unknown feature vector P has to lie within this min max hyperbox, then obviously I have to have the condition that V I has to be less than or equal to p I, which has to be less than or equal to w I. Okay. And this has to be true for all I varying from 1, 2 up to n. So, for all the components, all values of I, p I has to lie in between v I and w I. Okay. So, if it is so, then we can say that this unknown feature vector p that lies within this hyperbox or min max hyperbox given by the min points v and the max point w. Okay. So, this definition itself tells you that how to generate a min max hyperbox. That is, given a set of points, I want to find out a min max hyperbox which encloses all the points within that set. Okay. So, for doing that, what I have to do is I have to find out every component, the minimum value of every component among all the feature vectors which are there in the set. Okay. So, if I have 50 points within the set, for each of these feature vectors, I have to find out the first component. So, I will have 50 first components. Minimum of that will give me the first coordinate of the min point. Okay. Similarly, coming to the second dimension, I will get 50 components coming from 50 different feature vectors. I have to find out minimum of that. That gives me the second coordinate of the min point. Similarly, the maximum values will give me the corresponding coordinates of the max point. Okay. So, given a set of points, for every component, the minimum values will give me the min point and the maximum values will give me the max point. And you find that that follows from this particular condition, that if p lies within the min max hyperbox, then every component of p has to be within the minimum and maximum values of the corresponding components. Okay. So, within min point and max point, min component and max component of the corresponding hyperbox. Okay. So, by checking this condition, I can easily find out whether a point, an unknown point, belongs to a given hyperbox or not. Okay. Now, come to a situation that suppose I have a situation something like this. So, this is my x 1 dimension and this is my x 2 dimension. Okay. The hyperboxes are generated from the training samples, and as the hyperboxes are generated from the training samples, it is not necessary that set of hyperboxes that you generate that will cover the entire feature space. Okay. It is quite possible that a part of the feature space will not be covered by any of the hyperboxes, because it depends upon the distribution of training samples. Okay. So, suppose I have a situation something like this, that I have a hyperbox somewhere over here which belongs to class omega 1. Okay. I have another hyperbox somewhere over here which also belongs to class omega 1. Okay. I can have another hyperbox somewhere over here which also belongs to class omega 1, right. I can have a hyperbox over here which may belong to class omega 2. Okay. I may have a hyperbox over here which also belongs to class omega 2. Okay. I may have a hyperbox over here which also belongs to class omega 2. So, you find that given these hyperboxes, there is a lot of space in between the hyperboxes which is not covered by any of the hyperbox. Okay. So, if a feature vector, unknown feature vector, because these hyperboxes are created using the training samples. So, it is obvious that all the training samples which are given, they are covered at least by one of the hyperbox. Okay. But given an unknown sample, if an unknown sample falls somewhere over here, Okay. So, this is the position of the unknown sample. As this unknown sample does not belong to any of the hyperbox. So, should we say that this unknown sample does not belong to any of the classes? Okay. So, it is quite logical that if I can have some measure by which I can classify this unknown sample as well. Okay. So, one of the approaches what we discussed about the minimum distance classifier, that is you try to find out what is the distance of this unknown sample from different hyperboxes. Okay. So, by calculating the distance, you find out that which hyperbox is nearest to this unknown sample. Okay. And I can classify this unknown sample to the nearest hyperbox or the class of the nearest hyperbox. That is one of the way where we go for minimum distance classification sort of thing combined with this hyperbox classifier. The other approach is which appears to be more logical, because that is what is in line with how we think or how we classify without actual measurement. Okay. So, that is what is called fuzzy membership or fuzzy classification. I will not go into the details of fuzzy theory, but I will just introduce what is the concept of fuzziness and how this fuzziness can be combined along with our hyperbox concept, so that we can have a definition of fuzzy hyperbox or fuzzy hyperbox set. Okay. So, the concept of fuzziness is something like this. Let us take a simple example that given a set of persons, a large number of persons, we want to say that who are the persons who are tall, who are the persons who are short, and who are the persons who are say medium height. Now, while doing this, we never take a tape, find out what is the height of a person, and accordingly we classify whether the person is tall or the person is short. Okay. Or we also say that the person is very tall. Okay. We say that the person is tall, but not so tall. Similarly, short, but not so short. Okay. So, when we decide something or when we classify something, we do not really classify in the hard manner. Okay. It is not that if the height of the person is above 6 inches, he is tall. We never do that. But what we do is some sort of approximation, or given a set of classes, we want to find out that what is the likelihood that a person belongs to one of the classes. Okay. So, that is how we say that the person is very tall, the person is tall, person is not so tall, he is very short, not so short or short, things like that. That means, when we are doing some sort of classification, in our classification we are incorporating some sort of fuzziness. Okay. So, if I put it something like this, that so on the horizontal axis I put the height of the person, okay, and on the vertical axis I will put something like membership grade. Okay. So, our classification will be, or the classification rule will be something like this. So, if the person is height is between say 6 feet and say 6 feet 6 inches, I will say that the person is tall. So, this is the region when I say that the person is tall roughly. Okay. If it is between say 4 feet to say 4 feet 6 inches, we said that the person is short. Okay. and somewhere in between say 5 feet to say 5 feet 6 inches, we say that is medium or say standard. Okay. Because in India most of the persons are within this category 5 feet to 5 foot 6 inches, right. So, I can take this as standard or medium, right. So, the membership grade can be put something like this, that if the person is tall, I can say that these are 3 different sets. Okay. One set is tall, termed as tall, one set is termed as standard, the other set is termed as short. So, I just want to classify like this, that the whether the person belongs to this set tall or the person belongs to this set short or the person belongs to this set standard, right. So, if a person has a height which is within 6 feet to 6 feet 6 inches, then obviously the person is tall. So, the membership to this particular set tall has to be equal to 1. Okay. If the height is in between 4 feet and 4 feet 6 inches, the membership to this set has to be 1, that is maximum. If it is within this, membership to this set has to be 1, that is maximum, right. And you find that I have a lot of space between 4 feet 6 inches to 5 feet, similarly 5 feet 6 inches to 6 feet, similarly beyond 6 feet 6 inches, below 4 feet. Okay. So, these are the different height regions which are not marked as belonging to any of these sets. Okay. So, I will have a maximum value of say equal to 1, maximum membership grade equal to 1, and when the height is between 4 feet to 4 feet 6 inches, the membership given to this particular set is 1. Between 5 feet to 5 feet 6 inches, the membership given to this set is 1. Between 6 feet and 6 feet 6 inches, the membership given to this set is 1, that is the maximum. Okay. And the remaining region, it can be done like this. If the height is less than 6 feet, depending upon the difference from 6 feet, I can reduce the membership grade. Okay. So, I can have a membership grade something like this. Okay. So, over here in this region, let us consider say 5 feet 6 inches to 6 feet. Okay. If the height is say around 5 feet 9 inches. Okay. So, I will be somewhere over here at this position. Okay. So, in this location you find that the person gets 2 membership values in 2 of the classes. Okay. So, the membership value to class tall is this, to set tall is this much, the membership value to the set short is this much. Okay. So, this itself I can consider as fuzzy classification, because it tells me that what is the likelihood that the person is tall and what is the likelihood that the person is short. Okay. So, this measure itself, or that way I generate a vector actually. Okay. So, membership to class short, that falls to 0 at this point. So, at this point membership to class short will be 0, membership to class standard will be this much, the membership to class tall will be this much. So, actually I get a 3-dimensional vector, 3-dimensional vector of membership values to different classes. Okay. So, that is what is fuzzy membership vector. So, this fuzzy membership vector itself can be taken as the classification, which is called fuzzy classification. And if I want to make a hard decision, that is decide about whether the person is tall or the person is short or the person is standard, then what I have to do is I have to put a max operator. Okay. I have to find out what is the maximum of all these membership values, and the membership value to whichever class is maximum, I classify the person to that particular class. Okay. So, in fuzzy logic, taking this maximum operator is nothing but fuzzy union. Okay. So, fuzzy union gives you the maximum of the fuzzy membership values. On the other hand, if I take the fuzzy intersection, that gives me the minimum of the fuzzy membership values. Okay. So, as I said that I will not go into the details of this fuzzy logic or fuzzy algebra, but just for our application what is required, I am discussing that. Okay. Now, after giving introduction to this fuzzy membership values, let us see that how we can make use of this concept in our hyperbox classification. Okay. So, what I will do is, given this unknown feature vector, I will try to find out that what is its membership value to different hyperboxes. Okay. And that membership value or the set of membership values themselves can be used as the classification output, or I can find out the maximum of these membership values and I can classify this unknown object to the class of the hyperbox to which its membership value is maximum. Okay. Now, when I talked about this sort of membership profile, this membership profile is not unique. I can have other kinds of membership profile as well. Okay. This is what is simplest. Okay. The membership profile can be something like this. Okay. It can be a triangular membership, something like this. Okay. There are different types of membership profiles that can be used. Okay. So, this is triangular one, this is something like your Gaussian curve. What is mostly used is this sort of membership, that is trapezoidal membership profile. Okay. You find that this is nothing but a trapezium. So, what is most commonly used is the trapezoidal membership. Okay. Now, the question is that how do you compute such membership functions? So, we can consider in our case that say this point may represent our mean point corresponding to this particular class tall, and this point will represent max point. Okay. So, as we said that if the unknown feature vector falls within the hyperbox, that means within the mean point and max point, then the membership value to that particular class will be highest, that is equal to 1. As it falls beyond mean point or beyond max point, not within the hyperbox, the membership value has to be reduced depending upon its distance from the hyperbox, and the distance I can compute as distance from the mean point if it falls to the left of mean point, or I can compute the distance to be dispensed from the max point if it falls to the right of the max point. Okay. So, the kind of situation that I have is like this. So, let us say that this is where I have the mean point V, this is where I have the max point W. Okay. So, within the mean point and max point, the membership value that will be computed, that has to be maximum, and that is equal to 1. Okay. And beyond mean point and max point, the membership value has to be reduced, something like this. So, this is my, on this axis I have the membership value, and the fuzzy membership value is usually represented by mu. Okay. That is what is conventionally used. I can use some other later as well, that is not a problem, but if I use something else I have to define what I am using. But if I use this symbol, it is known to everybody that this represents fuzzy membership function. Okay. So, how do I compute this sort of membership function given the mean point and the max point, that is V and W? Okay. I am just writing in 2 dimension. Okay. Actually, I have multi-dimensional feature vectors. So, this both this mean point and max point v and w will be multi-dimensional vectors. Okay. So, if I define a function like this, so as I have multiple number of hyperboxes, okay, so I have to identify which hyperbox is it. So, suppose I consider a jth hyperbox and the membership function value that will be computed by this jth hyperbox is represented by bj. Okay. So, I have to get an expression of this bj, and bj will depend upon 3 terms or 3 of the three arguments. One is the mean point of bj, because bj is a hyperbox, that is mean point of bj which will represent as vj, the max point of the hyperbox bj which will be represented by wj, and our input feature vector which is a, because depending upon the position of the input feature vector, I have to find out what is its membership to the hyperbox bj. Okay. So, I can have a functional representation something like this, say bj arguments are, suppose my input feature vector a, okay, then vj which is the mean point and wj which is the max point. Okay. So, these are the 3 arguments on which this bj will compute the membership function, and this membership function can be computed like this. If it is an n dimensional feature vector, or the feature space that I have is n dimensional feature space, okay, then I have to compute the membership function considering all the dimensions, right. So, I define a function something like this, 1 minus f a I, that is ith dimension, minus w j I, that is the ith component of the max point w j, right. This max point w j is the max point of my jth hyperbox. Okay. Then a term gamma, I will explain what this gamma is. Okay. Minus f v j I minus a I and the term gamma. It is going out of the screen, right. So, like this, take the summation of this, because I have n different dimensions and this I am representing in ith dimension. So, I have the take the summation of this for I is equal to 1 to n to consider all the dimensions and take the average. Okay. But still this is not complete, because I have not defined what are these functions f, right. So, I can define this function f like this, that f x gamma, okay, this will be equal to 1 if x into gamma is greater than 1. Okay. This will be x into gamma if x into gamma lies between 0 and 1. Okay. And this will be equal to 0 if x into gamma is negative or less than 0. This is how I define the function f. Okay. Now, see what does it imply with respect to this particular diagram. If the point a I am considering only the ith dimension, okay, that is true for all other dimensions. If I consider the vector a, which is the unknown feature vector here, falls within the hyperbox, okay, I am considering the ith dimension. So, let me put this as V I, this as W I, and A I will be somewhere in between. Okay. So, if A I lies somewhere in between, that means A I will be greater than V I, but A I will be less than W I. Okay. Now, come to this term, A I is less than W I. Okay. So, A I minus W j I will be less than 0. Similarly, A I is greater than V I. So, V j I minus A I, that will also be less than 0. And in this functional definition, this x is nothing but A I minus W j I or V j I minus A I. Okay. So, both these terms being negative, my x into gamma, that will also be negative, right. Gamma is a positive quantity. So, this x into gamma, that term will also be negative. So, I am in this region, in this definition, because x into gamma is less than negative, is less than 0, it is negative. So, f x gamma, that becomes equal to 0. So, both these functional values f a I minus w j I gamma and f v j I minus a I gamma, both of them are zeros. As both of them are zeros, this summation or a single term in this summation returns me a value 1, which is summed over I equal to 1 to n. So, I get value equal to n, because this one is being added n number of times. Take the average, divide by n, I get a value equal to 1. Okay. So, that clearly shows that if the point lies between min point and a max point, then the membership value which is computed, that will be equal to 1. Is that okay? Now, let us come to the other case. Suppose the point lies to the left of V I. If the point lies to the left of V I, then A I will be less than V I, at the same time A I will be less than W I. Okay. So, if A I is less than V I, then this term is positive, because this is V j I minus A I and A I is less than V I. So, this term is positive. Coming to this term, A I is also less than W I. Okay. So, A I minus W j I, that will be negative. Since that this term is negative, so the value of this function is equal to 0 as per this definition. Whereas, value of this function will be either this or this, depending upon what is the value of V j I minus A I times gamma. Okay. So, if V j I minus A I times gamma is greater than 1, then the value of this f x gamma is equal to 1. If this value is equal to 1, then what does this term give me? 1 minus 1, that is equal to 0. Whereas, if V j I minus A I times gamma is in this region, it is between 0 and 1, then the output given by this term is 1 minus x times gamma. Okay. So, 1 minus x times gamma, what is x? X is nothing but the distance from the mean point. So, that is my x. Okay. So, it is 1 minus x times gamma, that means I get a straight line with a slope equal to gamma. So, that is this straight line. Similarly, if the point falls to the right of W I, okay, in that case, that means A I is greater than W I. A I is also greater than V I, right. So, A I minus W j I, this term will be positive, whereas V j I minus A I, this term will be negative. As this term is negative, so this functional value will be equal to 0. This functional value will be either this or this. So, if the distance from W j I of the point times gamma is very large, it is greater than 1, then the output will be 0. This functional value, the membership value will be equal to 0. Whereas, if the distance time gamma is in the range 0 to 1, okay, then the output is 1 minus this. Again, I get a straight line with a slope which is equal to minus gamma. Okay. So, those are these two different straight lines. Okay. Now, see what does this gamma do over here? over here gamma is the slope of the straight line, over here minus gamma is the slope of the straight line. That means, the gamma, this particular parameter gamma is indicating how steep this line is. Okay. If the gamma is high, then the straight line will be something like this. Sorry, if the gamma is high, then the straight line will be something like this. Okay. The slope will be very high. If the gamma is small, then the straight line will be something like this. And that is what indicates the degree of fuzziness. Okay. When the straight line is bending in this direction, that is, the slope is becoming more and more, that means we are moving more towards hard classification or crisp classification as it called. Okay. If the value of gamma is less, then the crispness or hardness is reduced, at the same time the fuzziness is increased. Okay. So, gamma is a parameter which controls the degree of fuzziness. If the value of gamma is more, the fuzziness is more. If the value of gamma is less, then the fuzziness is also less, right. So, using this particular expression, for different hyperboxes, I can compute the fuzzy membership function of this unknown feature vector to all the different hyperboxes. Okay. Now, to find out the fuzzy membership function of this unknown feature vector to a particular class, I will consider the membership functions computed by different hyperboxes belonging to that class. Okay. So, here if I consider that these blue boxes represent class omega 1 and the green boxes represent class omega 2, I will compute the fuzzy membership function of this unknown point from each of these blue boxes and take the maximum of these membership functions. That gives me what is the membership value of this unknown feature point to the class omega 1. Okay. Similarly, I compute the fuzzy membership function, fuzzy membership value of this unknown feature point from to each of these green boxes, take the maximum of them. That gives you what is the membership value of this point to this particular class. Okay. And once I get that, I get two membership values, one for class omega 1, other one class omega 2. Okay. So, these two membership value themselves, as I said, can be used as fuzzy classification. And if I want hard or crisp classification, then I have to find out what is the maximum of these two. Okay. And whichever is maximum, I have to classify this unknown feature vector to that corresponding class. Is that okay? Now, how does this algorithm will actually work? I have a set of training samples. Say I have capital N number of training samples, let us assume. These training samples are coming from different classes. Okay. So, if I have two classes, some of these N samples are actually taken from class omega 1 and some of the N samples are actually taken from class omega 2. Okay. So, what I will do is, I will consider these training samples one after another, and while doing so, I will go on creating the hyperboxes, right. So, when I consider the first training sample, I do not have any hyperbox created till that time, right. So, what I will do is, I will create the first hyperbox, but I have a single point. Okay. So, for the first hyperbox, I will put the min point and max point to be the same. That means, it is a point hyperbox, which is same as the coordinates of that particular feature vector. Okay. Then I consider the second point. If the second point, because I am considering the points arbitrarily, it is not necessary that second point will come from the same class. Okay. So, if it comes from the same class, then I have to go for expansion of the hyperbox. So, I have an initial point, then I have a second point. So, I have to go for expansion of the hyperbox to include this second point. If it belongs to another class, to the second class, then instead of expansion of the previous hyperbox, because previous hyperbox belongs to some other class. So, instead of expanding the previous hyperbox, I have to create a second hyperbox, again a point hyperbox, because this is the first point coming from the second class. So, I have to create a second hyperbox, which is again a point hyperbox, for which the min point and max point is same. Okay. And I have to go on doing that. Wherever possible, I have to expand an existing hyperbox to include the new point which is considered, otherwise I have to create a new hyperbox. Now, while I expand the hyperbox, then there is a danger. The danger in the sense, if I come back to this figure, yeah, see over here.
Sir, if any point is within a already within a hyperbox, that is within the maximum range,
Yeah.
then should we expand that hyperbox?
No, we should not. If it is already within that hyperbox, that means it is already covered. If it is not covered, okay. Suppose in this particular case, I go on expanding this particular hyperbox. If I expand this particular hyperbox, you find that it covers points from another class. Okay. So, when I expand an existing hyperbox, then there is a risk that the amount of error that you will incorporate, that will go on increasing. So, one extreme case is every point is considered as a point hyperbox. The other extreme case is all the points irrespective of its class belongingness is put into the same hyperbox. Okay. So, if every individual point is taken as a point hyperbox, I do not have any error. In the other case, I have maximum error. In between, I have error varying between maximum and minimum. Okay. So, if I allow the hyperboxes to expand in an unconstant fashion, then the risk of incorporating error is more. So, I have to put some constant on the way the hyperboxes can be expanded. Okay. So, anytime I get a new point belonging to the class of an existing hyperbox, I should not expand the hyperbox which is already existing in an unconstant fashion, in an uncontrolled fashion to include this new point. So, there should be some constant up to which I can expand an hyperbox, beyond which I cannot expand an hyperbox. Okay. So, I will stop here today. We will continue with this discussion in the next class. Thank you.